Alright, so we're very happy to have Konstantin Telemann here. He'll be here for the next 3 weeks or so. And he's giving a series of lectures over the next 2 weeks, one of our Perspectives in Geometry series. So the first lecture is today. And on Thursday there will be 2, one at 12:30, one at 3:30, and the schedule will be repeated again next week. All the lectures are in this room. And his title is Langlands Duality in Near Symmetry.
I had forgotten the title, I guess, so I gave a slightly different one on the notes. And I feel a little bit, well, I'd like to thank, I'm very happy to be in Austin. I'd like to thank you for inviting me to give a series of lectures. I feel a bit nervous because there are some experts in the audience on this topic. In fact, people have done, like David Benz-V, who've done a lot of work on this. That's far more sophisticated than anything I will say. I will be talking about much more basic story having to do with Lie group actions on categories. And for me, the surprise was that the Langlands dual group does show up, when in fact my thinking was that what I'm doing is so basic it should not. I mean, it has to do with actions of compact groups, which are analogous to finite dimensional representations. In finite dimensional representation theory of compact Lie groups, you don't particularly notice Langlands duality very well. I mean, it only appears when you look at more sophisticated things. But it does appear, apparently, when you look, instead of looking at actions of a Lie group, of a compact Lie group on a vector space, you begin to look at actions on categories. It appears quite natural. So today's lecture, I think, will be very basic, and I apologize to some people in the audience who may have seen similar lectures I've given in the past. In fact, it might be a little bit, the material might be a bit newer to me than it is to you, because I wrote up the notes late last night, so I'll see what came out. This May, I think, I was giving some lectures in Utrecht on a very similar topic, actually. At some point, I'm reading a theorem from my slides, and I stop and I realize I didn't know this. Actually, I was wrong. In fact, it was the reason why I was doing all the other things, but it was a 3 a.m. phenomenon, I guess. So I'm hoping that I've avoided this time around. So let's start by recalling a cartoon version of quantum field theory with target X. X is a space, a manifold, or lots of other things. So M is going to be space-time, and we have the time 0 slice, time 1 slice, so space-time continues to propagate. And quantum field theory will have a space of fields. These are the maps from M into space of classical fields, maps from M to a target space X, which is fixed. M will vary. And you have the space of maps as a restriction to the initial time boundary and the final time boundary. And if you look at the space of functions, slide up, yes. If you look at the space of functions on the space of maps from a fixed time slice to X, and you find a way to turn that into a Hilbert space by figuring out how to define L2 measure on it or some other method, then that is meant to be the Hilbert space of quantum states of the theory. And time propagation is going to result in a linear operator from the space at time 0 to the space at time 1. And the matrix coefficients of this propagator in the basis of delta functions, in the base of points on the space of functions, so to speak, is given by a path integral, an integral over a space of maps with fixed boundary values of something that's defined from a classical theory. If you can really pull this off, you're in luck. It almost never works, but except in dimension 1, really, very rarely in dimension 2. But of course, we have to remember the space of maps, restriction to the boundary, and in some way the notion of integration. Okay, that's what one is trying to do. And now let's move to a situation when the target space X has a group of symmetries. We call it G, and let's say it's finite, and if it makes life easier, you can assume it acts freely on X. And then, let's say that for some reason you're interested in understanding quantum field theory with values in the quotient space x mod g. That's really the space you're after. Maybe x is simpler, x mod g is more complicated, so you're trying to use x to get to x mod g. And that can be done in 2 stages by the gauge method. And what you do is observe that a map from M to x mod g corresponds exactly to an isomorphic class of principal G bundle on M and a section of the associated bundle with fiber x. So given a principal G bundle, you form the product with x and divide by the G action, you get a fiber bundle with fiber x over M. And then you can take this, that's what replaces the space of functions is the space of sections, and then that corresponds to maps to the quotient. So we're trying to do the path integral over this space. By the way, I'm happy to put the copies of the slide and make them available slides, paper. So at least today is not so essential to take notes, I would think. So then you can, as I said, you can compute the quantum theory in 2 stages. So first of all, you fix a principal bundle, and then you do the path integral over the sections of a bundle. And that would be called quantum field theory with a classical background field, which is the principal bundle P. If G is finite, really there are no fields, but let's ignore that for a moment. But then you can quantize the theory fully by also summing over the isomorphic splice of P's, and by the time you've done that, of course, you've summed over all maps to x mod g. But what you have to note here is that if the hope was to compute the theory for x mod g from that for x, it's not going to work. And that's because of the appearance of so-called twisted sectors in the space of states. Right? Because now we can have interesting principal bundles on the time slice at time 0, and we have to look at the functions of on the space of sections, and that's a new component of Hilbert space of states which did not exist before. So before, if you just had, we're looking at the print as a trivial G bundle, and sections of that is mapped to X. Even if you remember the action of G on that, you're only going to get one summand of the space of states. The space of states is going to be the direct sum of these over all isomorphic classes P of principal bundles. So this makes it impossible to recover the quotient theory or the gauge theory just from the original one and remembering the action of G. Something's really missing in the story. There's some exception we'll see in a second in 1-dimensional quantum field theory, and some exceptions in 2 dimensions in conformal field theory, but the 1-dimensional exception is the interesting one. So here's an example which you'll find a lot of literature on that, recent literature. If you find the Landau-Ginzburg model with potential W, a polynomial with isolated singularities at the origin, then the space of states for that is a Jacobian ring, or the Milnor ring of the singularity. The germs of functions modular partial derivatives of W. But if you have a group of symmetries and you want to study the gauge theory, you're going to have, in addition to the G invariant part of H, you're going to have twisted sectors HG, where you restrict to the G fixed points set in Cn, you restrict the potential as well and form the Milnor ring of that, and it's the sum of those that contains the space of states. If you just compute the theory for the untwisted sector, you will not have the information necessary to make the field theory. And actually that's the point of the literature. That's why this theory is considerably harder with a group of symmetries than it was without it. Now here's an example from geometry where G is a compact Lie group. So X is going to be a compact symplectic manifold, for example, projective algebraic, and G acts in a Hamiltonian manner. And there's a 2-dimensional topological quantum field theory, it does not depend on the metric on the surface, with target X. The Hilbert space of states, the cohomology of X, and some physics arguments which I personally don't understand explain that the path integral can be localized to a finite dimensional space of pseudo-holomorphic maps from a Riemann surface into X, and then it's a well-defined integral, and actually this is in fact a well-defined theory called Gromov-Witten theory. There are twisted versions of this as well. So one would like to gauge Gromov-Witten theory Why is that? Well, because it might be related to, the gauge theory might be related to a Gromov-Witten theory for the quotient of x by g. Now, the first thing you notice is that in this situation, where G is a Lie group acting on a compact symplectic manifold in Hamiltonian manner, there will have to be fixed points. So exactly what one means by quotient, which will be singular, is a bit unclear. But it turns out the belief, the standard belief, is that some limit, an adiabatic limit, of the gauge Gromov-Witten theory is related to the Gromov-Witten theory of the GIT quotient. And there are partial results in this direction. Some are quite old, going back to Gaio and Salomon, and Woodward and collaborators have more recent results on that. I don't want to say that the limit of the gauge theory is exactly the theory of the GIT quotient. There are some issues relating to how you define the compactification of the space of pseudo-holomorphic maps. And the compactifications coming from the gauge theory and the standard target space theory are believed to be slightly different. So what do I mean by adiabatic limit? Probably a lot of people know that. Well, one really needs to form a compact moduli space of principal G bundles and pseudo-holomorphic maps. And for that, it's easier to explain algebraic geometry, but you can do it without. To compactify a moduli problem, typically one needs a polarization and defines a moduli space by projective embedding. And there are two basic polarizations on this space. One of them ignores the target and remembers the bundle, and it's a theta line bundle. It's an ample line bundle on the moduli of G bundles. And the other one comes entirely from the target. Essentially, you pull back the Kähler form or the projective line bundle on the target by various points on X, and you can define from that a version of the tensor product of all this polarization labeled by the points on surface. So you can define something like, maybe I should write, you have evaluation at X, if you have from the space of maps from a surface to X, and then you can define something like a continuous tensor product of X, well, that's misleading, X is a point in S. You can define the continuous tensor product of the pullback of the line bundle. You have to interpret that it's going to be a determinant of a cohomology bundle. And it turns out to be semi-positive. And convex combinations of these guys are believed and known in some cases to lead to projective moduli spaces. And by adiabatic limit, I mean the limit where you move towards the polarization that's entirely pulled back from X. That will no longer be positive, will just be semi-positive. But the limiting space, it's reasonable to believe, should be related to the space of maps to the GIT quotient. Somehow, this polarization wants to make the map land into the stable part, semi-stable locus. This polarization is trying to make the underlying bundle stable, and that's not in this case what we're after. So we want to emphasize the second one. X is a compact symplectic manifold. I don't think anybody has there are very strong results in that situation. In the algebraic situations, there are better results projected.
Could X be like CP1 with U1 acting on it?
Yeah, it could be that.
And what would this thing you were saying about the adiabatic limit, in that case, what would it mean?
Well, in that case, the GIT quotient is going to be a point usually, so presumably you're going to take the limit and the limit of the invariance, the gauge invariance you compute, and if you do things right, you're going to get a Gromov-Witten theory of a point. The cases that actually have been studied more would be, lying a bit, because in a sense this is what we'd like, but it makes life difficult. The cases I've been studying more are when X is in fact affine, for example, a vector space. X itself doesn't have pseudo-holomorphic bubbling. That makes the theory a bit easier. That's certainly the one that Salomon studied. I don't know if Woodward has now moved on to non-exact examples. But yes, so in that case, sort of the project in this form doesn't make sense. You're not going to study the gauge theory of P1 in order to discover the point. But maybe that gives you some constraints on the gauge theory of P1. We go the other direction.
So what should we think as a model X?
X.
We're trying to
Well, for example, let's say X is a vector space and G is a torus, then the GIT quotients of those are toric varieties, some of which are projective. In fact, all toric varieties arise this way, and essentially all the known results, and the Gromov-Witten theory is pretty well known, and better in the Fano case and in other cases, and all the results can be traced to the realization of the GIT quotient, all the known results. In fact, I'll use that example, I think probably on Thursday. I'll discuss how you get the torus to write in the Foucault category of a toric variety coming from a vector space. So I don't know what the Foucault category of a toric variety is, but I'm going to write something down. Okay, what does this page want to do? Oh, yes. So that relates to the problem I mentioned earlier, that you cannot hope to recover the gauge theory just from the ungauged one in action of G. Well, the main exception is when space is a point. Not the target is a point, space is a point. So it's a one-dimensional quantum field theory. In that case, there are no twisted sectors because every G-band, principal G-band on a point is trivial. And it's easy to describe the theory. So what are we going to have? We're going to have intervals of time, and we're going to look at principal bundles at the ends of the intervals are fixed, so the initial and final states, and it has to be continuous and principal G-band on the interval, so all the information I have is a group element, which tells you how you choose the isomorphism between two trivial bundles. So this, the classical theory with background field G, must lead to the action of the group element G on the space H. So H sits here. This with G must define an operator that gives an action of G. If you take a closed space-time, so space-time is a circle now, time goes in a circle, then you have to specify a classical background, the principal bundle with holonomy G. Actually, this will be defined only up to conjugacy. And to that, you define an invariant, and the invariant is going to be the trace of this operator you had before acting on H. And saying that the gauge theory is computed correctly by summing over a principal bundle is actually just a little theorem in topology. Because first, summing over a principal bundle level of spaces means taking sections of the bundle H over BG or taking invariants, the same as co-invariants. And the path integral for the circle, summing over all possible isomorphic pairs of bundles, is going to be the sum of the traces of the possible holonomies divided by the automorphism group of the holonomy. I should have written it more obviously. The sum over conjugacy classes, that's a bit more obvious written like that, of trace of the conjugacy class, and now that's divided by the order of the centralizer of the group of automorphism of the bundle. So you weigh them down by group of automorphisms, but it's the same as the sum on the left, which by a known theorem is the dimension of the space of invariants. So in other words, you get a correct formula by saying that you can gauge the theory and obtain you can gauge the theory by a path integral over possible principal bundles. Or if you like, a different way, it confirms the fact the space associated to the gauge theory must be the space of invariants, the quantum space. So in this case, we had no problem recovering everything just from H and the G action. But that was, of course, before there were no twisted sectors. So what made it work was that we knew the theory was on points where there are no twisted sectors. All G bundles are trivial. And thankfully, thanks to recent progress in topological quantum field theory, at least in the topological case, we know how to do that for more general quantum field theories. We understand two dimensions especially well, but there is a great theorem in any dimension that tells you what it means to define a topological quantum field theory, not just for time slices, but for time spaces with boundary and with corners as well, so for manifolds with corners. And the statement in 2 dimensions is that the TQFT is generated, I'll explain a little bit of that later, by a linear category C. That means an additive category with C-linear space of morphisms and bilinear composition. I don't mean to say, just to make it clear, that there's this action of C on objects in the category. So the category of vector spaces would be a perfectly fine category. And this category must satisfy some strong finiteness condition. Lurie calls this 2 dualizability. And we can spell them out reasonably easily in 2 dimensions. The first one, dualizability, is an analog of finite dimensionality for vector spaces. It says that there exists a dual category, which is essentially the linear functors from C into vect. And it's a reflexivity condition that sees its double dual. It's more or less what you're asking. And that's fairly easy to satisfy, meaning it's reasonably easy for a category to be reflexive, doubly dual in this sense. I mean, you have to be a little careful exactly what conditions you put in the category and what kind of functors you have. There are various to do that. But that was the easy part. And the more subtle part, the strong finiteness condition, is the existence of an automorphism, a linear automorphism of the category called the Serre automorphism. It's defined by the condition that might be familiar from algebraic geometry, from Serre duality. It says that the dual of the space Hom of xy, the C dual, is a space of morphism from y to the Serre functor applied to x. So in the case of, say, vector bundles on a projective variety, the Serre functor would be tensoring with a canonical bundle and also a shift in degree by plus or minus a dimension. So for vect on x with x projective, Serre is tensoring with kx and shift by, I forget. That becomes the Serre duality theorem. And Hom, in that case, it doesn't make a lot of sense unless Hom means the derived Hom, meaning all the cohomology. There's another, as a footnote, there's another condition you can ask. You could ask that this Serre functor should actually be the identity, and that corresponds to the canonical bundle being trivial, well, except for this little n here, which let's leave out. And that's called the Calabi-Yau condition. That makes the category even better. By the way, I can get more specific if it's necessary, but only if people ask. I don't want to sort of jump into detail unless I get a request.
How could we know what to ask?
Sorry?
We don't know what to ask.
Well, you could ask me, give me an example of one dualizable category which is not too dualizable or something. So I mentioned that, say, one dualizability was actually easy to satisfy. In fact, if you take any algebra over C and take the category of, actually of all modules, you have to be a bit careful, that will be dualizable in this sense. And the dual category is not going to be exactly this, unless you massage the definitions. The dual category will be the modules over the algebra with the opposite multiplication, if it wasn't commutative. So on the other hand, the second condition is very strong, and you can prove that if the category was abelian and it satisfies all this, then in fact it's semi-simple with finitely many simple objects. So among abelian categories, there are essentially only trivial examples. The reason there are interesting examples is because they come from derived categories, from differential grade or derived categories, such as coherent sheaves on a smooth projective manifolds. The other example that's meant to exist is, and is proved in some cases, a Fukaya category of a symplectic manifold, of a compact symplectic manifold. All right. So as I said before, if you just know the TQFT, if you know what it does, what it assigns to circles, say, and surfaces, if you know this Hilbert space of states and the linear operators and the action of the group on it, that's not enough to get the gauge theory. But now I claim that if you know it for the point, that should be enough. And here's the strategy for recovering the gauge theory if it's been defined, or the structure has been defined all the way to points. Yep. So you have let's assume you have a TQFT that's generated by a linear category C which satisfies the conditions I discussed earlier. So first of all, I mean, it must have an action of G. So I forgot to say that, otherwise you can't gauge it. G must act on the data. Given an action of G on C, you can try to form the categories of invariants and co-invariants, or rather invariant and co-invariant categories. It's like the fixed point category, the quotient category. We'll have to define those things. And you can hope that just like for a vector space, if you're in characteristic 0 and G is a finite group or a compact group, you have an isomorphism from the invariants, the co-invariants, that actually will be necessary to get the dualities to work properly. What you have almost tautologically, just like for vector spaces, is that the dual space, the space of co-invariants, the space of invariants in the dual. And there is a statement of that form, but that's not enough. You need a stronger statement to get things to run. And then at the end, you hope that the fixed point category, or the quotient category, also satisfies the duality conditions and therefore generates a TQFT. And of course, the final hope is that that is the gauge TQFT. I didn't say that. So hope that, for example, for finite groups, that the invariants, say invariants for surfaces, the numbers you compute from surfaces, are obtained by gauging the original TQFT. And this turns out to work actually well for a finite group G, well, at least with the usual constraints that you work over a field whose characteristic doesn't divide the order of the group. I mean, that condition was true even with vector spaces. You'd have trouble right here. So surely it's going to show up. No. So, well, I'll come back to that in a second, but when I said, I should have mentioned it earlier, when I said TC generates topological field theory, in particular, I'd better produce a Hilbert space of states, and that indeed, there's a little theorem you can prove that under the reconstruction procedure, the space of states associated to a circle, it's the only space you have, is a Hochschild homology of the category. And it turns out, we'll rather return to that, that for the quotient category CG, the space of states is the sum of twisted sectors, and I'll have to explain that in a little while. All right, any questions for this? Because this more or less is the program. This is what we're going to do and why we're going to start discussing group actions on categories. We want to construct a gauge TQFT. And
last step, if you have these first steps, do you expect the last step to be easier or harder?
I mean, this last step, I think for finite groups, they're all easy. For if you think of the example of the Fukaya categories, I still don't know an example of Gromov-Witten invariants computed from Fukaya categories without a group, let alone when they're gauged. So if your goal was to use this to compute something, some invariants, I don't think we're there yet. So, but the problem is not the group, the problem is that we don't quite know how to do it.
What if you're in a situation where somehow you already have a gauge theory lying around, and then you have this one that you rebuild from what's assigned to a point, and you want to compare it to the original. So So what you get for free is a map from the sort of formal one to the one that you start.
So you had a theory that was not defined down to a point, say, but had a gauged version, and then you have the category and you construct the fixed point or quotient category, and generates a field theory you would like to say they're isomorphic. Well, it's not so easy. The only overlap you have, of course, is in the space of states. So, but I think even in string topology, which is a completely algebraic theory, it becomes a delicate question to what extent there's a similar question. To what extent the operations at chain level are determined by the operations at homology level, and there are partial results along that. And this is the same sort of result, because the group action is a refinement of the operation, which would be obvious if everything was defined rigidly at chain level, but has possibly been lost by the time you pass to homology. So in terms of how easy it is, there are some basic operations you have to compare, unfortunately. So if you really honestly mean the theory defined over the modular of curves, then somehow you have to compute both sides. I mean, that's okay. So I mean, I don't know if that's what you had in mind, but I remember another example: string topology versus Floer homology of the cotangent bundle. And people just compute the operations and compare, as far as I know. There just isn't a scheme to. There isn't a scheme to do it directly, unless you know that both sides are generated by a standard procedure from the categories. I mean, of course, there are theorems in that situation about the categories, about the Fukaya versions of the Rath-Fukaya category being the same as the category of modules over the ring, which generates string topology. I don't think I have a good answer to the question.
Costello's construction, for instance, comes with some sort of universal property.
Right, because his definition of a TQFT is slightly different. I didn't actually give any definition of a TQFT, but it's slightly different from the one I'm implying here. So there is one definition of a TQFT in which everything is determined by C, all the operations, including the space. So he has a slightly weaker gluing condition, and then I think you can have compatible TQFTs which, I forgot if come with maps to or from the Hochschild homology, are compatible with the operations. But it's some tweak in the axioms which changes one to the other. I think nowadays this is more fashionable just because it really satisfies its property. If you know what you've done, what structure you assigned to a point, you know the rest. So. But in that example, of course, if you had that map being an isomorphism, you are done. The structural map. The operations have to agree from that point on, in Kevin's case. Okay, any other questions to which I do not know the answer? No. All right. So let's start with, it's going to be very, very basic, but let's start discussing group actions on categories, and today I'll discuss finite groups, and then we'll have to move on to Lie groups and see what that means. So C is a category. It could be the category of modules over an algebra. That's good enough. And to define an action of G means that for each group element, have to give a linear functor. Everything would have to be linear. From C to itself, and you'd like it to be an action. So the product of group elements should correspond to the composition of functors. Now, when you act on a vector space, you compose the operators on one side, you take the operator for the composition on the other, and you check whether they're equal or not. Now, when you move to a setting of a category, functors can be isomorphic in more than one way. So what used to be a condition before is now data. You have to specify an isomorphism between the composition of functors Fg composed with Fh and the functor you assign to the product Gh. And I should have called this alpha because it's like something known as an associator. It's a bit like that, but. And actually, there is a way to think that there is no such thing as a condition. Everything is data. But sometimes data must be picked from a set which is either empty or has only one element. At that point, data becomes a condition. If the set has one element, I mean, it's a condition. So there are always conditions. So there's always data to give. You have to specify an equality between the matrix, the product of the two matrices and the matrix on the right, in the case of group action of vector space. But of course, either they're equal or not, there's nothing to specify. But if you can do it, then the condition is met. So I mean, if you're willing to work with infinity categories from the start, the distinction between conditions and data evaporates. I mean, everything is much easier. All right, so what else do we want? So we want an isomorphism here between the f of the composition of functors. I'm also going to insist that the functor assigned to the unit is exactly the identity. And now there's a condition. The condition comes in on this isomorphism, on the data that's been specified. So that's a typical pattern. When moving from vector space to linear categories, the place where we used to meet conditions, you have to supply data, and there's one condition later on to supply. And the condition comes from the fact there are two ways to go from the composition of the three functors to the functor associated with the product. Because you can compose the first two, and then you can use phi for that, and then you can compose then the first composition with the last one, and that itself is a composition of phi's. Or you can compose first the last two, do nothing the first functor, and then compose the first one with the result. And a priori, if you just put random things here, these are different. But the condition is now that actually these agree.
I'm sorry. Just have a really elementary question.
Yes.
I understand what an isomorphism between categories is. What's an isomorphism between functors?
An equivalence between category, right. So maybe now I do need a board. Right. So probably I should have started with that. So if you have a C and D, you have two functors f and g. What does a functor do? So a functor assigns to x an object, an f of x in D, and to some morphism from x to y, a morphism in D. That's a functor. You can have two such functors, and now is the notion of a natural transformation which you could also think of as a map from f to g. And this is the assignment for each object in C. Well, what do you do with an object? Well, you can send it to f of x, or you can send it to g of x, the two objects in D, so objects in D. I should need a name for this. T, maybe. And the datum of a natural transformation is a morphism Tx from f of x to g of x, which is compatible with everything you can write down. Any diagram you can write down commutes. So there's going to be a g of y, a g of phi, an f of phi. If you take two elements, an f of y, this will be ty, and you're asking that going this way or this way, the same thing. You preserve the structure. So there is a notion of a map between two functors which is not an equality, because you have morphism in the target category from f of x to g of x. And now an isomorphism is of course such a datum or each Tx is invertible. So if this is invertible, then the inverse is also a natural transformation. At that point you say that you haven't specified a natural isomorphism. Intuitively, maybe the closest to the intuition is these are topological spaces, these are maps, and we're looking at homotopies between maps. That's that'd be the analog of a natural transformation. The downside of that is that sort of they're always invertible up to homotopy, so it's a bit misleading, whereas in general it's a strong condition for a natural transformation to be an isomorphism. But in terms of the structure of the arrows and diagrams, that's perhaps the first thing to think. You have spaces, maps, and homotopies between maps. You can also have homotopies between homotopies, but that's because spaces are like infinity categories, so we're not going there. Unless there's popular demand, we can talk about group actions on two categories. Actually, I'm confused about that, so I couldn't. So maybe an example, just to show that there is something to specify. Okay. It's coming up as an exercise. Maybe we can work it out, but I'll probably screw it up. So let's take the category of vector spaces. So that's a bit like the ground ring where we're working now. I mean, it has a multiplication, a tensor product in addition to the sum. If you have another linear category, you have an object, you can tensor it with a vector space simply by taking a sum of copies of itself. So it's a bit like the line, the analog of a line. It's one-dimensional. Okay, so let's take this category and let's define an action of G on it by setting all the functors to be the identity functors. So it looks like you're defining the trivial representation, the trivial action, but that's because you forgot that you also have to specify an isomorphism between compositions. Now all the compositions in this case are the identities. The identity is the identity functor. So what's a natural, it's an exercise somewhere. So phi gh for each pair G and H must be an isomorphism from the identity functor to itself. So that means what? It means that for each vector space in vector space, you need a phi gh from V to V. But now we have some properties such as linearity, which says that if V is a direct sum of lines, and every V is a direct sum of lines, the phi gh you specify must be a direct sum of what you specify for each line, phi gh on each C. So actually, all you're specifying once and for all is an isomorphism from C to C. That's a complex number. So the conclusion is that the automorphism of the identity functors on vect are C star. And if I roll the endomorphism, I will get C. So what looks like a huge amount of complicated data is actually just in this case just one number, which is required to be non-zero. But I do have to specify such a number for each pair of, yes sir, thank you, for each pair of group elements, and these numbers are subject to a condition as square here, and the exercise I'm assigning is that the condition is a group co-cycle condition. That phi gh is a 2 co-cycle with values in C star. I'm not doing the exercise for you because I don't have in my mind the group co-cycle condition. If you do look it up, you'll find that it's equivalent to this. I mean, I could write it down by copying it from here, but I will not be doing the exercise. Or I could look it up on Wikipedia very quickly, but that also works. All right. So I'll state a theorem which I won't prove because it's proving me is really making the statement precise. Linear actions of G on the category of vector spaces up to isomorphism are classified by elements in the second group cohomology of G with coefficients in C star. And that is the cohomology class associated with this cocycle. In other words, there's a notion of isomorphism for group actions on vect, and under that notion of isomorphism, if two cocycles differ by a co-boundary, then the corresponding action becomes isomorphic. But the proof of the theorem is really spelling out clearly what this means, and then you just check the condition.
But here you were looking, in your exercise you considered only group actions for which Fg is the identity for all G.
Yes, that is correct.
So I might have thought that there would be a lot more linear actions where it's not.
That is a good point. It's not completely obvious. You're right. Can I do a 5-second argument?
Yes, where does the dimension of the vector space come from? You take one
The
of
elements
the
are
vector space.
All the functors are tensoring in the vector space, and since it has finite order, the vector space has to be a line.
It has to be invertible. Yes, thank you. Yes. Thank you. Linear functor, that's right. Linearity again. Thank you, yes. See, I'm told there are people in the audience more expert at this than I am. So I wanted to contrast this with the statement of linear actions on G on the line C, namely they're classified by the first group cohomology, the coefficient C star. And if we were to continue that, you could define a notion of a projective action on a category with C star cocycles, and you'd find the possible cocycles are classified by H3 with C star coefficients. So somehow whereas projective representation of G on vector space, we have a cocycle in H2. So by making the group act on categories instead of on the categories instead of vector spaces, the classification by cohomological data shifts up in degree. Actually, this is a much simpler answer we might have expected given the complexity involved in going from vector space to category. All right. So now if we know what an action is, that's the analog of a linear representation, I would like to define the invariant and co-invariant categories, or co-invariant or quotient category or cross-product category sometimes called. So let's start with the invariance, a bit easier to write the definition. Actually, it's very easy to write it incorrectly, and I think I just did that. But it's almost correct. I think there's a phi GH somewhere, which I meant to check which one it is, and I forgot apparently. So, ooh, this thing goes in my shirt. Wow. All right. Trying to distract attention from the mistakes. All right. So if we are acting on a set, I mean, the invariance would be the points are fixed by the group action. That's because the points of a set are either distinct or not. And we're asking a condition. We're asking that g of x should be equal to x. We're asking, is it equal to x or not? If it is, then it's fixed by g. If it's true for all elements of g, it's fixed by the entire group, capital G. So now, as before, what used to be a condition has to become data, because two objects in a category could be different but isomorphic, and they could be isomorphic in many ways. So a fixed point will be an object together with a collection of isomorphisms f sub g indexed by the elements of the group. The isomorphisms have to relate x with the transform, actually that was fg of x in the previous page's notation. fg composed with f sub fg. Okay, I think now I'm good. G of fh. So this is not the subscript. All right. So the isomorphism must be compatible with the fact that, well, the group elements multiply by a group rule. There are relations in the group, and they tell you that the isomorphism, roughly the isomorphism corresponding to a product Hg is a composition of the corresponding isomorphism, the only way in which it could make sense. And the part I forgot comes in because, of course, composition is not strict, but is mediated by this isomorphism phi, and the same isomorphism has to appear on one side or the other of this, and I'm not going to try to figure out. Sorry, I should have done it at home. Got a 50% chance of getting it right if I pick one. So it's pretty good. So these are the objects of the fixed point category. That's when you say an object is fixed if its transforms under the group are isomorphic to the original object, but isomorphic in a way that's coherent with respect to the group action. And what are morphisms between two such things? Well, these in particular are x's are objects in the category, so there are morphisms between them, but now you want the morphism to be compatible with all the extra data you are supplying. So for example, you have an x, have a morphism y, but you also had, we'll call it f sub g to fg of x. You had a morphism well, this depends on x as well. Now I want to put a dependence fg x, maybe fgy to capital Fg of y. Fg was a functor, so there's an Fg of phi on this side. So we're asking that this should commute. So phi is a morphism in CG if this diagram commutes. If not, phi is not acceptable. We'll break some data and you'll try to do algebra with the usual rules and something will go wrong. Very simple.
What should we carry around this equation?
For the fixed point category,
I mean, for what? I mean, you know, like if you're talking about manifolds, you say two manifolds. I mean, what's the intuition for what these things are?
yes, I mean, without getting to the example, you'd like to say that the action somehow is internal. So G acts on a category, but the objects you might want to think have internal structure. And the fixed points are those on which G can be represented in the internal symmetry of the object.
If your category is just vector bundle on X on a manifold,
Yes.
then the fixed points are exactly at the very vector.
Yes.
I mean, you know, if I can think that way, I don't have a problem.
And what's
I should
the-
just extend my notion of thinking that.
So finite group X on the manifold with X on the bundle is what I pull back, and then saying it's invariant is lifting the action to X on the bundle.
Okay. First example over a point, right? So C is vector bundles over a point. G acts trivially, and really mean trivially now means the cocycle is trivial. So the identity and the identity maps. And then the fixed point category is the category of representations of G. Because in this case, Fg of x is the same as x, strictly the same as x. I'm asking for it to be the identity. And then what I'm asking is that G should be a linear endomorphism of, linear automorphism of the vector space x, and all these should compose correctly. There's no phi G in this case. You really ask. So G is represented by automorphism of x. So the objects are representations, and then the next condition is that you only allow linear maps which are compatible with the action of G. Just says that, well, this is by definition the category of representations of the group. All right. Let's make it a little bit more interesting. Let's take the category of vector space, not the trivial representation, just the identity functor representation, but with an interesting cocycle. And in that case, the category you get, well, there's only one guess you could come up. How could you change the notion of a representation if you have a two cocycle with values in C star? Well, you could ask for a projective representation with cocycle phi. If you pick a co-cycle representatives. And that's what the answer is. And this time, that's what we'll be saying. Again, this is a map from X to X. But now in the composition law, instead of having a strict equality, you will have a co-cycle coming in, which says it's a projective representation. So another example, I'm slowly building up to the example David gave in like 3 seconds, sorry. So take vector bundles on G with a translation action. In this case, the G fixed point category is just vector spaces. Because if you know sort of the fiber at the identity, you must come with identification data with all the other fibers as part of the condition. And in general, of course, G acts on X. C is the category of vector bundles, then the fixed point category of G equivariant vector bundles.
Does vex G is vector bundles on G as a set?
Here, vector on G as a set, there's no other structure, it's just a category, so we're not putting a structure on it. Is that
I
what?
just mean that notation just means on G.
Yes, vector bundles on G, so here vector bundles on X, yeah. That's right.
So the idea is we're going to start with the category and reduce everything to fixed points.
Right, so I mean the idea for gauging thing, well, if you know the category which generates your quantum field theory, then the fixed point category should generate the gauge. Okay. And it's a not difficult theorem for a finite group is the point, but for a Lie group it's a little trickier, so. But I only know it to be true in examples for Lie groups. All right, so, okay, any more questions about the fixed point category? I'm sure a lot, but any questions I can answer?
What is that X?
X is any space, so G acts on any space X. Could be a set or a manifold or anything you'd like. And then the fixed point category is... So what happens with this condition is sort of if Fg moves X, then you're going to supply an identification of X with a moved point. So really there's no more data coming from the moved point, you're removing that. If Fg didn't move X, then in fact you're supplying an automorphism of X. So somehow you're identifying things in an orbit, but representing the stabilizer by the internal symmetries. That's what you're doing. I think it's very clear in the case of vector bundles. All right, okay, so now the next one is actually, in the special case, very easy, but it's harder to write. I hope I wrote it correctly. Easy to miss conditions. The quotient category. And we can ignore the parentheses, has to do with good behavior later. The category, the quotient category, will have the same object as those of C, but now we have to sort of mod out by the action of the group. But modding out the category doesn't, you can just identify things, you have to supply identification data. So that means we're going to add isomorphisms to our category. Namely, for each object X and each group element G, we're going to add an isomorphism, a new arrow from X to G of X. So declare there is an isomorphism. So it's a new generators for morphisms. And there are relations. There are the kind of obvious relations that well, first they compose. You go from X to G of X, and H of G of X, and you want to say that the new generator that goes directly is a composition of the two steps. And secondly, you want to say that they commute. This used to be called F sub G, right? And for some reason they've been called G. That they are well behaved with respect to the G of X is also F sub G of X, right? Okay. Well behaved with respect to the functor Fg, and this tells you roughly that you can move this new morphism from the right of a morphism to the left of some other morphism in the obvious place. So going this way is the same as going that way. So right composition with one of these new arrows can also be written as a left composition. And it's not cross G. I think that would be true in a nonlinear case, but I think it's C of G tensor with that. So from these relations, I mean, I didn't put linearity here yet. And if you stay with that, what you're doing is you're augmenting the space of morphism by a factor of g. If in the linear case, of course, that's you're tensoring with a space of functions on G, because you can take linear combinations, require that. So I didn't say linear, did I? Didn't say linear anywhere. It's probably okay though as it stands. And the linear case, remember that you have to linearize. So here in linear case, we're going to get functions on G tensor morphism.
Isn't it that we have our old arrows and then we add a new arrow for each group element in each object, each pair?
Yes.
So the new morphisms, the old morphisms plus the group across the objects.
No, because you can compose one of these guys with one of. But I'm telling you that's all you can do, because compose on the left you can also write as composing on the right. They're not disjoint. It's actually an instant. This is very confusing written this way, but there's an example everybody probably knows, and this is just.
Is there like a clean definition of like the quotient is some other category together with a map from your original category that's such that?
There is a universal description. Yes, that's right. Characterization of it. It's a co-limit of the categories indexed by a diagram given by G, and the other is a limit.
Use at this level of, I mean, or is that actually, is it just easier to work with the actual construction?
It depends what you want to do. I think if you want to prove, for example, that the dual of the co-invariants are the invariants in the dual, it's easier to use a characterization. But if you want to compute what the answer is, you're probably not going to do it by using a characterization. So, but here's an example. I mean, this is what it's trying to say. But I think I agree. Probably would have been helpful to say, for some people, it would have been helpful to write the characterization. So let's look at the category, which has a single object, and the endomorphisms are, they're just taken to be the complex number. It could be an algebra. Then with a trivial group action on this, the quotient category also has one object, but the endomorphisms of that are the group ring of G. In general, if you had an algebra C, you would have as endomorphism algebra A, C of G tensored with A, but if you allow G to act non-trivially on A, you would get the cross-product algebra. So what this does is the observation that the cross-product algebra construction works for a category, and it represents the quotient category. All right. So, what am I talking about here about co-kernel completion? And I talked about here the finite co-limit completion of, or co-kernel completion of. Well, that has to do with finding the right kind of categories which it's convenient to do algebra. And if you ask for absolutely nothing about your category, you can have surprises. And it's a choice always, but one setting that's emerging as being useful is to look at linear categories which are co-complete, they're closed under arbitrary co-limits, and functors which are co-continuous, preserved co-limits. And for example, if you start with this category, well, there are lots of projectors inside the group ring, which factor out various irreducible representations. If you ask for the category to be closed under forming co-kernels of these maps, you're going to be adding all the representations of the group G, and in fact you'll end up with a category of its representations. So as a general nonsense construction, we start with this very simple small category and produce the representations of the group. I jumped ahead because I wanted to make some easier results first. So first is that the dual of the co-invariants is the invariant part of the dual, and that can be checked from the definition too or from the characterization. The second, a bit less obvious perhaps, is that if C is dualizable and G acts linearly, then the invariant part of the dual is a dual of the co-invariant. And the more interesting part is that if you're in the characteristic 0 case and you work in this context where you add co-kernels, then just like for vector spaces, the co-invariants and invariants are equivalent actually. And that's not completely obvious. But it's not difficult, but it's not completely obvious. And finally, what allows gauge theory to work for a finite group is that, I'm not going to even try to prove this, that if C is too dualizable, and you're in this situation of characteristic not dividing the order of the group, and you're completing, and you're taking co-kernels, then the fixed point category is also too dualizable, so it generates a topological field theory. And the space associated with the circle, a priori, general nonsense tells you it's a Hochschild homology of this new category, but it turns out to be a sum of twisted sectors for the Hochschild homology of a functor that was called Fg, assigned to the category, the invariant part of it. And here's a small remark that might confuse everybody, though, that algebraic geometers may recognize that. So if the original category is Calabi-Yau, it may or may not be the fixed point category is Calabi-Yau, because the action of G may not preserve the isomorphism of a self functor of the identity. In other words, if you have a Calabi-Yau manifold, the group action on it, it may or may not give the rise to Calabi-Yau quotient. If it acts non-trivially on some fibers of K, for example, you're in trouble. So what I was going to do next, but I will do it only by popular demand, is have a refresher on Hochschild homology of a category. I think it's not strictly needed. I mentioned it before because I mentioned you can reconstruct the space associated with the circle from the category, and that's how you do it. But I don't think I'm using that anytime. So unless there's a strong cry for this, I'd like to go back to gauge theories for finite group, mention gauge theory for a compact Lie group, and explain the plan of what I'll discuss in future lectures. Yes?
So there's this category that only had one object and it's isomorphic over C.
Mm-hmm.
Is it like does it play the role of the trivial object in representation theory that
Well,
from the or variance from it?
It does, but I prefer to think that vect plays the role of the unit line, because see, this is not closed under sums, right? I mean, I'm not allowing you to form the sum of two copies of the object star somehow. It's like the category which contains only, if you like, one line as the object, but you're not allowed to form the sum of two lines. So it's not quite. It breaks some of the condition we'd like to have, but I mean, it is true. What you said is true. You could characterize it the way you said.
So you can describe invariance
Yeah.
as just a function of some trivial categories.
Yes, but you're right. I would like to say it's functors from linear functors from vector with a trivial action to C. That's correct.
And state your thing again, the case for vector spaces, whatever this covariant.
Which the definitions here.
No, the theorem.
Which theorem?
What I meant, that this thing, that after completing, you said for a vector space.
This one. This one.
The analog for vector space.
Right. So a vector space, if you're in the characteristic, doesn't divide the order of the group. You have a map. Well, I can write it here. Look at that. The invariants sit inside the vector space, which projects to the co-invariants, and then it's very easy. It turns out this map is actually an isomorphism if characteristic 0 of car K does not divide the order of G. So you'd like something. It's true in this case too that the invariant maps as a functor to C and maps to CG, but it's not quite true that the composition is the equivalence. You have to do something to it before it turns to an equivalence. And that has to do with, maybe I don't want to explain this now, but okay, let me say one word. The composition turns out to have an action of G by automorphism of the functor. And if you take the co-limit of that, then it becomes an equivalence. And that's why we need to take the co-limit completion there. Otherwise, you can't construct the equivalence between the two.
So I guess an example is you work out both sides. You take the trivial category and something invariant to representation.
That's right.
It's generated by the
Yeah, so you cannot factor that's right, you cannot factor, that's right, you cannot even write a map if you took the examples I wrote before you take the co-limit completion. And if you cannot factor the functor through the forgetful functor that forgets the action of a group, that would lose information. But you can remember the action of a group. It's another one of these funny things about categories, okay? So the fixed point category is an equalizer of lots of maps from C to C labeled by the group elements. And the quotient category is it's called the co-equalizer on the right. It's a universal thing which makes this commute. So by the time you travel this way, this map, in all possible ways, all the maps are equal, no matter which route you take to travel. The maps are equal for two different reasons. So, sort of the map is invariant for two reasons, and that means it has an action by automorphism. So when you go to categories, I'm not doing nothing twice, he's doing something. It's an ideal world. Okay, I didn't hear a hooray for Hochschild homology, so I'm inclined to skip that. We can always do it later. So
What is Hochschild?
Okay.
I vote against it, but I want to know.
Okay. Here's the first definition, which you'll definitely not like. But then there's a definition that actually says something. So if C is a dualizable category with dual denoted by C check, typically this is going to be some nicely behaved linear functors from C to vects, like linear maps. Then, by definition of duality, it means we have a diagonal morphism from vect to C tensor C check, or a diagonal inside, if you like, and the trace or an evaluation pairing from C check tensor C to vect, subject to the adjunction conditions, which says that starting with C, moving by a diagonal to this big thing and contracting the other two factors gives the identity, and the same for C check. And if you replace C by V and think of it as a vector space and write for delta the identity and for this the pairing, this is exactly right, just repeating the symbol. And given that, by definition, the Hochschild homology is a composition of the trace to the diagonal. That's a functor from vect to vect, so it's tensoring with a vector space. And if C is two dualizable, it follows that it's finite dimension. But that's not very useful for seeing. Well, it's a trace of a diagonal, the self-pairing of a diagonal. So T is this a pairing evaluation of trace. Right? If it was a vector space, the Hochschild homology would be its dimension. Let's put it that way. All right. So it's something like a dimension, except it's a vector space instead of a number.
So what sort of object is it?
It's a vector space or a complex in general if you work in sort of a derived world. But let's write down explicitly, actually, in an example. No?
No, do it.
Sorry? Then that's what, well, that means the content of Thursday's lecture will remain a mystery. So let's take A modules of an algebra A. In that case, it turns out that the C-check dual category, which satisfies this relation, has modules over the opposite algebra. And the diagonal has to be a
module.
In this case, a module over A tensor A op, and it is A. It really is a diagonal in this non-commutative world, if you like. If A was commutative, it literally would be a diagonal in spec of A. And the trace takes an A tensor A op module and tensors it with A over A tensor A op. And if with these definitions you can check that, if you have patience to write it down, you can check that actually these are the identity functors from the category of A modules to themselves.
So it's a module.
Well, delta is a module and T is, well, delta is a module and T is sort of tensoring, with the operation of tensoring with a module. So now when we come, so T is that, so T of sense M, I haven't used this color yet, M goes to A tensor over A tensor A op with M. So M has to be in A tensor A op mod. So this delta takes a vector space to a module and tensors the vector space with a module A. This T takes an A tensor A op module and essentially restricts it to the diagonal and takes the sections and remember just the vector space. So if you work it out, I mean, if you start with A and apply with delta and apply the functor, you get A tensor with A over A tensor A op. And if you unravel the definition, that the space, the algebra A modulo its space of commutators. And that's a zeroth.
So that's
that is a zeroth Hochschild homology of A. Or of A modules. And there is a derived version of it which writes a zeroth homology of a complex, and which comes from a free resolution. To compute the derived tensor product, you have to resolve this guy as a free module. There's a standard resolution. So this is a zeroth homology in a complex. If you work with complex, you need the rest. And for those who like, I wrote down the definition for a category which repeats essentially this construction.
The question is really what is it? I mean, so it's a vector.
It's a vector space or a complex
Or a module.
or a great vector space. No, it's a vector space always.
Although the way you wrote it is it's an operation.
It's an operation from, it's a linear operation from vec to vect. But right, and that's a tensoring with a vector space, yes.
Okay, tensoring.
Tensoring with a vector space, the operation. Yeah.
That's a good one.
Yeah.
And it's an operation.
Yes, you're good. I mean, I can't disagree. All right, where are we here? How are we doing? Well, maybe if I only have a couple of minutes, rather than rushing through gauge theory for a finite group and the beginning of Lie group, let me tell you what I'm planning to discuss. Well, what's missing is, of course, gauge theory for a finite group and the compact Lie group. There's a debate. And then after that, we'll have to define slowly what it means for a Lie group to act on a category. And that will turn out that there's a surprise. There are two different definitions, one of which are two variations you can take. And they lead to very different styles of, if you like, algebraic geometric physics, namely the A model and B model in mirror symmetry, of mirror symmetry phase. So one type of action goes with the A model and another type with the B model. I'll discuss the torus in detail. We'll see a Langlands dual torus showing up. I mean, it's a baby appearance of Langlands duality. And you can interpret it as a sums version of a Fourier transform. And then we'll discuss some examples of toric varieties. And then I want to move on to the surprise. And the surprise is going to be the failure of ordinary homological algebra to compute correctly fixed point categories. That's homological information. And this comes from the fact that at some point we'll be forced to abandon the Z grading in the theory and move to a Z2 grading. And this is an operation that's not very well understood. We don't understand Z2 grade homological algebra well, I think. And that will lead to what I call non-perturbative features of the theory. Kept me for a long time from talking about this because I was computing invariants of zero and getting not zero, which is kind of bad. And finally, I'll propose a slightly geometric interpretation, a semi-classical picture of this story that involves holomorphic symplectic manifolds and Lagrangians inside, and can replicate some fixed point calculations that can, as I said, not be done by just homological algebra methods or get the wrong answer. And here we'll see a Langlands dual group for a non-obedient group showing up in a surprising way. All right.
Questions? Okay, so let's thank Constantine again and we'll resume on Thursday.